Hey there, astronomy students. Wrong one. Okay, so this is the Milky Way Part 2, and let's just jump right in. Okay, so we're going to talk about the history of the Milky Way. Where do they think this thing came from? All right, so the traditional theory is that it was a quasi-spherical gas cloud of that fragmented into smaller pieces, forming the first metal-poor stars or population 2 stars. All right, and then this cloud was rotating and collapsed into a disk-like structure. And later populations of stars, population 1, restricted to the disk of the galaxy. Okay, so that was the original thought of how the Milky Way had originally come about. Well, how did that change? We now know ages of stellar populations pose a problem to the traditional theory of the history of the Milky Way. So, possible solution for this is that the later accumulation of gas, which could have been due to mergers with smaller galaxies, right? And we recently discovered that there are rings of stars around the Milky Way which may be a remnant of such a merger. Pretty cool, right? Okay, so where would that ring of stars be? Right here. Nice. Okay, notice that the sun is nowhere near the center, which is the halo, or not the halo, the bulge, but it's actually on the outside in one of the spirals, right? Oh, I just turned. Okay. All right, so we have O and B associations. Here are your O and B stars, right? Those big, luminous, young clouds. They can be found in the outside in the arms, the spiral arms of the galaxy. And the distances to these O and B groups or associations can be used or can be found using the Cepheid variables. Okay, we learned about those. Yes. All right. O and B associations trace out 3 spiral arms that are near the sun. So we have 3 arms of the spiral that have O and B associations, which are young, hot, bright stars that are near the sun. Pretty cool. All right. The Orion Cygnus arm, the Sagittarius arm, and the Perseus arm. Okay, here's a radio view of the Milky Way. If you were to take a, here, let me come back here for just a second, just to talk about the spiral arms. Okay, most massive stars, which live short lives, live in the spiral arms. They're scattered along the spiral arms, and the spiral arms are known as the places of star formation. I think I covered that, but I'm not sure. Just want to make sure I cover it all. You can trace spiral arms through the neighborhood by using spiral tracers, which are O and B stars. And here we go. Astronomers use radio telescopes to see through all the gas and the dust. So why would they use radio telescopes? Well, radio waves have a lower energy. They don't get deflected as quickly, so they can make it through all the gas and the dust. And that's why we are able to see from this radio view, we're able to see all of this here in the middle because there's a lot of gas and dust in there, but the radio waves can get through. So here's a radio map of a wavelength of 21 centimeters that traces all that neutral hydrogen that's inside of the Milky Way. Okay? Like I just said, interstellar dust does not absorb the radio waves because they are lower energy, so you can use those to see what's inside. All right, 21 centimeter radio observations reveal the distribution of neutral hydrogen throughout the galaxy. So there's neutral hydrogen all throughout the galaxy, and the distances to the hydrogen clouds can be determined through radial velocity measurements. So the Doppler effect, you send something out, wait till I see how, okay. Let's see. Next one. Neutral hydrogen is concentrated in the spiral arms of the galaxy. So, tracing these molecular clouds. Radio emission of the CO, or carbon monoxide molecule, is how you can find the molecular clouds. In some directions, many of the molecular clouds are going to overlap, and the clouds can actually be disentangled using that velocity information. So, here's just a picture of a bunch of stuff. Okay. Molecular clouds are actually concentrated or can be found in the spiral arms, right? Molecular clouds are places of star birth, and they say that the stars are formed in the spiral arms, so you should be able to find molecular clouds in the spiral arms. Oh, check that out. All right, so structure of the Milky Way is revealed. Distribution of stars and neutral hydrogen can be found all along the place, right? I'm going to be honest with you, I don't have any clue what that is. That picture, anyways. It's just probably an infrared vision image of the Milky Way from, well, it's not our Milky Way, it's another galaxy that looks like our Milky Way that they use to compare, because we've never actually gotten outside of our galaxy and taken a picture of it. So everything that we say about our galaxy, we only know based on what we're doing by comparing it to another galaxy that is a spiral galaxy. All right, but we now know that it is a spiral galaxy. Okay, it has these nice little waves. Star formation happens in the spiral arms because shock waves from supernova will ionize the fronts or ionize the gas initiated by these OMB stars. Remember the tracer stars. Okay, and that triggers star formation. Okay, spiral arms will be stationary shock waves. So as the spiral arms are moving, that's creating those shock waves, which starts that star formation that we learned about in those last couple chapters. All right, so how does this happen? Well, spiral arms are basically stationary shock waves. The stars and the gas clouds orbit around the galactic center and they cross the spiral arms. As they cross the spiral arms, it initiates that star formation. And the star formation self-sustaining through OMB ionization fronts and supernova shock waves. So this is self-sustaining star formation, acts to modify the arms with branches and spurs at the birth of massive star triggers. It triggers the formation of more stars by compressing the neighboring gas clouds. All right, so what happens, the nature of these spiral arms? Well, these spiral arms appear bright when you have newly formed massive stars against the dark sky. They're dark against the bright background of a large galaxy. So it depends on what the background is. The chance coincidence of small spiral galaxy. This is just a picture of a small spiral galaxy that we have seen in front of a large background galaxy. So here in the front, we have a small spiral galaxy, right? And in the background, there is a large spiral galaxy. Okay, all right. Let's see, spiral galaxies. Grand design have two dominant spiral arms. Okay, so here's one, and here is the other. Two dominant spiral arms. The flocculent or woolly galaxies have spiral patterns, but no dominant pair of spiral arms. So you can kind of see the spiral coming out off of it, but you don't really see the dominant spiral arms like you do in the grand design spirals. All right, so self-sustained star formation and spiral arms. The star-forming regions get elongated due to differential rotation. Remember, the ones that are closer go faster, ones that are further go slower. Okay, and star formation is self-sustaining because of those supernova shocks and the ionized fronts of gas that are there. All right, another type of galaxy that we can see is the whirlpool galaxies, a grand design galaxy. Self-sustaining star-forming regions along the spiral arm patterns are clearly visible. You can see along these spirals here, we've got lots of star formation happening, lots of active star birth areas. Okay. Oh, yep, there we go. All right, and the galactic center. So the galactic center, if we were looking, well, we can look at the galactic center from Earth because we are not the center. We are looking towards the galactic center, but we won't be able to see it in visible light because there's a lot of gas and dust all over the place, right? All right, so we would have to actually observe it in a different radiation, but we do get extinction by large magnitudes. Only 1 out of 10 to the 12th. That's like, we're thinking trillions, I think. 1 out of every trillion optical photons actually makes its way to Earth from the galactic center. All right, so from the galactic center, if we looked at it through radio imagery, you can see there's many supernova remnants. There's shells and filaments all over the place. Lots and lots of supernova remnants. So if we were to take that and blow it up, look at that. Oh, isn't that pretty? Okay, so SGRA is the center of our galaxy. That looks like a pretty dark spot, doesn't it? All right, here's an arc coming out through there. And then if we were to take that and blow it up some more, look, here is some more great stuff for us to look at. Okay, so SGRA is, again, the center of our galaxy. The galactic center is going to contain or they believe it contains a supermassive black hole that's approximately 2.6 million solar masses. That's what they say. They don't know for sure, but based on everything that we've seen, remember, in order to see these black holes, we're looking for not darkness, but we're looking for those X-rays and those radio waves and being shot off before the matter is pulled into the black hole. Okay, so that's why they believe that there is a black hole, supermassive black hole, in the center or the nucleus of our galaxy. Okay, so the nucleus it's completely invisible at visible wavelengths. We saw that. But if we look at it through these radio, infrared, and X-ray, okay, so this one would be radio, infrared, and X-ray wavelengths, that radiation can penetrate the gas and dust, and that's what shows us that there's these stars and all this dust on the inside of our nucleus of our galaxy, and they think that the very center has this black hole. Okay, they think that it's marked by that radio source, which was the SGRA, that would be the Sagittarius A, and the core, they say, must be less than a few astronomical units in diameter. Okay, but the motion of the stars around the center show that it must contain roughly 2.6 million solar masses, and a supermassive black hole is the only object that could contain so much mass in such a small space. Right, so they know this by following the orbits of these individual stars near the center of the Milky Way and have determined that it has to be a black hole. That's pretty cool, huh? All right, so here's some X-ray vision, that was cute. X-ray view of the galactic center for the Sagittarius A, and it says that regions there contain many black hole and neutron stars and X-ray binaries, but again, they don't know for sure. They do believe that it's a supermassive black hole in the galactic center. Yeah. All right, and hey, look, that's it. So, I'll see you in class, okay?